Good afternoon. Can you all hear me?
Good afternoon, madam. Yes, we can hear you.
Yeah. There are about 11 students. Normally, how many students join online? Is this count? Would like to start? How many students register for this course? I mean, to this subject. How many students follow this subject? Any idea? Anyway, there are 11 participants, so I will start the lecture. Even they can follow the recording later on, so we will start. So today we are following the distribution system engineering EE 662 subject. In this subject, we are going to cover the section distribution management systems. I think you all can hear me. Can you all hear me?
Yes,
Yes,
madam.
Yeah, so today we are covering the section on distribution management systems. I am Champa Dharmakirti, currently working as Director Transmission Operation and Maintenance Node in NTNSP, National Transmission Network Service Provider Private Limited. But I have about 10 years experience in distribution also, even though I work for transmission network service provider at the moment for about 2 years in transmission. So we will proceed to the lecture. The content of this section has several parts, customer information systems, and then modeling and analysis tools. Under that one, we will discuss about topology analysis, distribution load flow, load forecasting, state estimation, and distribution management system applications for system monitoring, system operation, system management, and outage management. So this is a typical power system layout, kind of traditional one, where we have generating station. Thereafter, the step-up transformer. Normally, generation happen in if we consider large scale um, hydros and thermal in kV kilowatt range, like 11, 13, like less than we can see less than 20 kilowatt is a typical one, typical value. So then we step up those voltages to transmission level voltages. In our country, it's 132 kV and 220 kilowatt. Then after that, the transmission power happened. We increased the voltage, generated voltages into transmission level voltages in order to reduce power losses along the line and voltage drop. Then at grid substations, after long distance transmission close to the load centers, we step down those voltages to low voltages. Distribution voltages in our country is 33 kV and 11 kV. Some industrial customers are even connected in these voltage levels, big customers. Then we step down those voltages further down. In our country, there are some cities still feed by 11 kV network, Anuradhapura and Kandy, as far as I know, and Colombo also. Some parts because of low voltage underground cables are there. Not only because of the underground cables, there are some overhead lines also um, distributing 11 kV voltage level power transfer. And after that, close to the this customers, like in villages or in industries, we step down these voltages further down to voltage volt level, from kilovolt range to volt range, either 33 kV or 11 kV to 230 volt. We call this happen in a distribution transformer. So at that level, there are customers connected in distribution feeders. Now we are going to discuss about the characteristic of distribution networks. Normally, these distribution networks are built as mesh circuits, but they operated radially, and their topology changes frequently during operation due to fault and maintenance. And the structure of the network changes as the network expands. So I will explain this stuff with the typical network. By the way, if you want to clear anything, you can stop me at any time and ask questions. So this is a typical network. It's a real network with greater power in Hinguragwada, that Min area, Abarna, that area. So I mentioned you that our distribution feeders are particularly 33 kV and 11 kV networks are built as mesh arrangement, but they operate radially. To explain you that if you can follow this diagram, this the grid substation which feed the whole network. From here, this you can follow my cursor. It's travel like this, and once it come to this area, there's a loop here. You can see there's a loop. What happened is this is arranged as a mesh circuit, but this is not operated as a mesh circuit. There's always several switches placed around this mesh. I will show you. If I expand, zoom it out, you can see. I think now you can see there. This is the loop I consider. Here, the power coming in this way, and here in that way as well. And you can see several switches. These are this S-shape. One is DDLO, and this is air brake switch, and this one is load brake switch. So what will happen is there's always normal open point. See here it's mentioned as normally open. In this arrangement, there's a normally open location. normally open. That means this is the most frequently used arrangement. That means power coming like this and end at this point. In this place, in this node, power coming from this node and travel like this and coming up to this one and coming up to this one here. And this end at this point. So this is the normal operating point, but this normal operating point changes frequently due to maintenance. That means, say, for example, there's a maintenance in between these locations. So what we can do is we can switch on, switch off from here and switch off from here and isolate this section and carry out our maintenance. At that time, power up to this node is coming from this way up to here. Is it clear what I have explained to you? So like this, due to different reasons, this configuration of the network change due to operational requirement, due to faults. This arrangement frequently change. That's what is mentioned in the lecture note. This one also a typical network. You can see how this feeders are arranged in a loop, and there's like before there is a place called normally open place. Then you can clearly see in this one how power flows in different loops, but always they operate in a radial manner. So normally there's a normal open point. Distribution, still we are talking about characteristic of distribution systems, distribution networks especially. They are extensive. Why it called extensive? If you consider now, every single house in this country is fed by distribution line. So you can think how much vast the distribution network is. And it is complex. It's not easy to uh, monitor, control, and analyze as well as manage because of this extensiveness and complexness. Again, real-time monitoring and remote control are very limited in these distribution networks. It is limited to big customers, bulk consuming customers, and like load break switch and air break switch. Up to that level only, it's remote controls are available. Beyond that one, even in distribution transformers, we don't have uh, ability to control. System operator intervention is required during fault and normal operation as well as during system emergencies. We need to have a system operator. No automated arrangements are there. Difficult to deal the complexity with manual procedures. However, these complexity also difficult to handle with manual procedures. Now, this is a different subject. So, if we consider our early distribution networks, they were designed to receive power from transmission network and to deliver to distribution customers. That means it had a unidirectional power flows. But at the moment, with the integration of distributed energy resources, especially solar, we can see bidirectional power flows. This is an example in a transformer which has 40 kilowatt solar penetration in a village transformer. The values given here are kVA values, which are average in 15 minutes intervals. Green color one is import, and blue color one is export. If there is export in that particular 15 minutes interval, it's shown as shown in blue color value. So you can see early in the morning, 1 o'clock, 1 a.m., 2 p.m., 2 a.m., 4 a.m., like you can see it's consumed power. That means importing power from the transmission side. And once it reach 7 o'clock in the morning, around 7, close to 8, it is start exporting power. You can see in between, you can see even it importing power. Maybe this may be due to cloud effect, or maybe that at that point of time the load has increased beyond the solar generated generation. So in some 15 minutes interval, it had changed from import to export. You can see both green color and blue color nodes are there at this point. So it means that during that 15 minutes interval, transformer has changed its mode to import to export. So by about 3 o'clock in the evening, that solar production has declined, so it has changed its mode to export to import mode. So you can see peak demand period around 8 here. So in our distribution network, this is the reality in many transformers now due to solar penetration. This is not the rare case. In many transformers, we can see this type of load variation throughout the day. Most recent daily demand variation curve is shown here. You can see how solar is coming to the picture nowadays. This dark brown is coal generated power, this base load, and the blue one is major hydros, and this brown one is coming from thermal generation, thermal oil, and solar. You can see how much solar and wind is limited, but this is the real nature at the moment in our network. This is not the reality only for the distribution network. This one is our transmission network. I will show you our new Anuradhapur grid substation, where we have 220 kV and 132 kV transmission line end up, and few distribution feeders are going out. So I will show you the You can see this is our new Anuradhapura grid substation where we have feeders from Lakvijay, that means coal power plant, Kotmale, Mana, and thereafter this that green color network is 220 network, and it stripped down to 132 network here from these two transformers. Those are 150 MVA transformers. There are two, and it then 132 feeders going out to Haparana, that are no all Anuradhapura grid, Putlam area, Vavuniya, Trinku uh, is giving uh, sending power to these areas. That means upper part of the country is served by these feeders. Vavuniya, Trinku, northeast side power transmission is happened by this Vavuniya and Trinku lines. But recently, when I visit that grid, I found the power flows. It's amazing that reverse power flow is available in transmission network also. I will show you the power flow in one of these transformers in the next slide. See, if you look into these values, the time is, these are very recent values. The time is around 16, I mean 4 o'clock in the evening. You can see that one of the 132 transformer is having -4 megawatt even at the evening. Now that solar generation is declining now. At that time, it's having negative. That means it power not importing but exporting here. And once it reach around 7 in the evening, you can see the megawatt is 68 megawatt. So we can see this type of fluctuations throughout the day, even in transmission networks at the moment. Even you can observe the voltage values. Even around 4 o'clock is 133, 132 kV lines. You can see the voltage as 134 kV. And at the peak time at 7 o'clock in the evening is 129 kV. So this is the nature in even in the transmission network at the moment. So recently we had an amazing thing. One of these line from Anuradhapur to Vavuniya, there are two lines. We had to switch off one due to maintenance work. So in the in the evening around 2 o'clock, we had to face a situation. The power, the current flow is going to exceed the line capacity. Line load limit is going to reach, but it is in reverse direction. So at that time, system control center switch off some major solar unit which feeds power into the network. Otherwise, we have to trip the line. That line will be tripped due to overload in reverse direction. So this is the real situation in the network at the moment, not only in the distribution transformers, even in the transmission networks. So this is the place I mentioned. This is the new Anuradhapura substation which you have seen the network. So these feeders are the one that from new Anuradhapura to Vavuniya line was that overloaded line. So if that trip all the transmission power transmission up to Chunna, Jaffna area, Kilnoch, northern part of the country will disrupt. So major solar producer has been switched off during that time in order to avoid feeder tripping due to overload condition. So if we consider this is 2024 statistical digest of CEB, you can see the power produced from major hydro it's 31%, but solar has come up to 10%, one third of that one. And so here the only solution for this one is to have battery or kind of storage. Now it has considered to install battery storages in major scale one and small scale one. These are two major scale one which are going to install in several locations in the country in the coming years. And there will be a pump storage also, which is one. There were some feasibility studies and identify there is a feasibility of installing 600 megawatt pump storage in Mahaoya. I think it's in Aranaik site, and Vavatan one also 700 megawatt one, which is close to Victoria power station. So this type of storage facilities only we can have that issue solved. Just for your information. And we were talking about the characteristic of distribution network. So when we consider distribution network, when we consider the three phases, which they are often unbalanced. You can see current flow in a transformer in a several 4 consecutive days, you can see how the current values are varying. They are not balanced. It's not easy to balance even because consumer behaviors are unpredictable. There's limited communication between elements of the network, and most controls are local. And if we consider comprehensive monitoring, it will generate very large amount of data because we have many. That network is massive. When we consider the load compression of a distribution network, it's complex and it's not well known. And the load consumption pattern varies dynamically with time. The load variation trend is more difficult to predict compared to the transmission network. So you can see this is a typical distribution, load curve of a distribution transformer. Not the load curve, but the current consumed by distribution transformer in several consecutive days. You can see the pattern is not similar, no, it's varying. This may be in a weekend, but the pattern is varies. It's difficult to predict. But when it comes to transmission, this load curves are pretty much similar. We have a morning peak and evening peak. So these are little bit formal. I mean, it's easy to predict. But when it comes to distribution network, it's not easy to predict the load profiles of transformers in distribution sector. And when we consider the characteristic of load, it's interesting, it's very difficult to predict. So one example is given here. This one is from a transformer in Kakirav area. this you can see that the blue is importing, the red one is exporting here. So like before, this is 15 minutes average import and export demand, maximum demand. So if you can see around 10:30, transformer has changed its mode to import to export. Again, around 1 o'clock, it has changed its mode to import to export. And when I check the load curve for several days, I found same thing is repeating. And I want to know why this type of changes are there, because it's every day it's repeating. Then I came to know that this one is this transformer is supplying to a factory, small factory that carrying out production use of coconut shells. So this is their tea time and this one is their lunch time. So once they switch off their machines, due to the installed solar, rooftop solars, it has changed import to export mode only during these time intervals. So you can see the voltage also during those two occasions, that voltage levels are increasing. No? See, otherwise it's having low voltages in the feeders. And other thing is, if we consider obtaining measurements of load in distribution network, it's not possible to obtain simultaneous measurement of all the loads. And further, those load measurements normally are insufficient and may contain large errors and bad data. The correlation between load is not well understood. So to give you an example, so these were some values we obtained during load balancing of a transformer. Even it is difficult to balance the load, but we try our best to balance the load in distribution transformers to reduce power losses and improve voltage profiles for the customers. So these values were obtained in 2021 when I was working as energy management engineer in a transformer. I think it's close to Mardan Kadwala. So we have a meter installed in in every transformer. We can get the total load of the transformer in LV feeders. All LV feeders are all the current in LV feeders are measured and it is given in this first row, transformer total, but it doesn't measure neutral current. So these A phase, B phase and C phase current are given in this row in one particular day. And these F1, F2, F3 are feeder currents. That transformer has 3 distribution feeders. That feeder currents are given here. But this one is automatically we can get it from install meter. If we want to measure the current exactly at one time interval, we can get that one even from my office computer. But to obtain the field current, we have to go to the feeder current, we have to go to the field and measure the current one by one in the 3 feeders. So it may take a few minutes. We have to get the feeder current in R phase, B phase and C phase in one particular feeder, and then we have to climb to other side of the transformer and get the feeder current of other feeder, like that. So it consumes several minutes. So if you consider these values, you can actually I got the transformer total from the meter, and subsequently we get the values within few minutes in a different in feeders also. So you can see when you see these current values, we actually the values are taken within few minutes. So they are not simultaneous measurement. But so because of that, you can you can see that they may have errors and even bad data. Even we don't know whether they are bad data or not, because it's not easy to predict. For example, if you come to this side, transformer total current is 85, and if we when we measure, feeder 1 has in A phase, feeder 1 has 62 amp, feeder 2 has 3.6 amp, and feeder 3 has 61.1 amp. So these three should be summed. If you get the summation of these three values, it should be equal to the transformer total. But it's not so. This 62 value may be erroneous, or maybe even it's true. We don't know. There may be a instant load, like for example, that happened one time when I take the load measurement at one to load balance in the feeder. All of a sudden, the value has gone high in one place. When I go to the load uh, travels to the distribution line, I found a twice mill, but it's operating in a single phase mode. So once they switch on these machines, only current increase only in the one feeder. So this may be due to some kind of load like that. Still, we don't know whether this one is the accurate one or not. So what we have to do is repeat the measurements and check whether there's any correlation in different days. That's why we have repeated the measurement in 3 consecutive days to find is there any way of balancing the load in these feeders. So, and now we are going to a section to talk about the transformation of power distribution. Climate change and global warming require decarbonization. I think you are familiar with these words now. The globally accepted decarbonization strategy is to electrify most of the human activities to the extent possible. So how we are going to do this decarbonization of the energy sector is to electrify most of the human activities and then decarbonize the electricity sector. We are trying to electrify the human activities and decarbonize the electricity sector. So what are the sectors to electrify on fast track? Which transportation, industrial, and agriculture. So we are going to electrify the transportation, industry, and agricultural sectors in order to decarbonize the decarbonization strategy. So this is required to limit global temperature rise, renewable energy increasing at the to limit the global temperature rise, we need to increase the renewable energy integration. So, as we have discussed so far, we require to be smarter than before to accept that much of renewable energy. Transformation of power distribution. Now, after a century of focus on centralized power generation and creation of massive electricity grids, today the focus is towards the decentralization, with the consumers becoming prosumers. You may have heard this word, prosumer. Producer and consumer. Consumers have become both. They have acted as both the producer as well as the consumer. So we use the term prosumers. The grid that designed to build for one-way flow of electricity is now experiencing bidirectional energy flow. That what we have seen so far. Now the debate is on whether to invest in transmission or in storage. As I explained to you before, the choice between generation, transmission and distribution and distributed generation, storage and distribution is clear. The merit toward the dispatch has advanced towards an energy efficient and environmentally responsible dispatch. So our dispatch method has changed by now. Grid of the future is where both power and information will flow in both directions. We need to have both power and information flow in both directions to have this control. So our early power sector, power distribution or power network has no IT on that. But now it has reformed from zero IT to IT centric age. Not only power flow in the network, but also information also required to be flow in both sides, both directions. Transformation of power distribution. The traditional grid's ability to monitor and control power flows in real time is limited to SP network. Okay. In the LV network, the power system operator has no visibility on who is consuming how much electricity as well as when and where they are consuming. In our traditional network, that was the situation. But in a smart grid with the smart sensors and smart meters, which are connected to computers in the control room, it is possible to remotely monitor and control the power flow of electricity in real time to every customer or even to every smart appliances inside the customer premises. So this is the smart grid which we are looking for. Okay. Now with this introduction, now we are going to the core of the subject section, which is distribution management system, DMS. Okay. So what's a distribution management system? Distribution management system is a collection of applications used by the distribution network operators, we call DNO, to monitor and control the electricity power distribution networks efficiently and reliably. You need to emphasize on this word. What are these? Distribution management system is a collection of applications, okay, used by the distribution network operators to monitor and control. And for what purpose? To make the power distribution network efficiently and reliably, to monitor and control the power distribution networks efficiently and reliably. You want to know these words well. So, what are the aims of the distribution management system? To improve reliability and the quality of the supply, to improve efficiency and effectiveness of the system operations, to manage, assist, absorb more renewable energy, identification of losses, monitor and control power flows in real time, to provide new services to customers, to achieve greater customer satisfaction, peak load management, self-healing grid, automated ways of removing temporary fault. Self-healing grid means we are implementing automated methods to remove temporary fault for detection and isolation and restoration, DIR. So these are some of the aims of a distribution management system. Development of distribution management systems. Anyway, do you have any question from the section which I have already covered? Please ask if there is any questions at any time. So, the development of distribution management system. If we consider history, the first generation of DMS integrated number of simple applications into a computer system. An interactive graphical user interface added to visualize the network. But the subsequent use of large relational databases allowed the management of more complicated distribution network and a large volume of data. What's a relational database? It stores and provides access to data points that are related to one another. And user can then obtain a view of the database to fit their requirement. Distribution management system includes number of applications that use modeling and analysis tools together with data sources and interfaces to the external system. That DMS application require modeling and analysis tool. For that one, we need input to that application. What are the inputs? Network parameters, customer information, and the network status data. Like that. Structure and main components of a DMS. You can see in this diagram, it displays the structure and the main components of a distribution management system. It has a graphical user interface, and there are many applications. For example, for system monitoring, network topology monitoring, network state monitoring applications, distributed energy resource state monitoring applications, and when it comes to system operations, network reconfiguration applications, void and power management, relay protection and recon coordination applications, and operation of distributed energy resource applications. And when it comes to outage management, fault identification application, fault diagnosis and fault location identification applications, supply restoration, and event analysis and recording applications are there. And for system management, AF, AM, FM, and GIS, that means automated mapping, facilities management, and geographical information systems are there. And field crew management applications are there. And there are operator training simulator also. And in between this graphical user interface, applications, and modeling and analysis tools. Modeling and analysis tools are there. For that one, we feed data from the network, data sources, and associated external systems such as SCADA. From here, we feed data into modeling and analysis tool. Applications are processing them and give outcome to the graphical user interface. Modeling and analysis tools include distribution system modeling, topology analysis, load forecasting, power flow tools, fault calculation tools, state estimation tools, contingency analysis tools, route optimization for field crews for breakdown attending, and reliability calculation tools. This type of things are there. So this is a structure and main components of a distribution management system. Purpose of application used in distribution management system. The applications are used for system monitoring, operation management, outage management, asset management, inventory control, keeping plant records, drawing and mapping, automated mapping, facilities management and geographical information systems. Design and planning of network extension to determine optimal expansion plan to achieve system reinforcement at minimal cost. These are the purpose of implementing application using the demand management systems. What is called automated mapping, facilities management and geographical information systems. We shortly call AM/FMM GIS. It allows utility users to digitize, manage and analyze network data. In this one, precise location and engineering information of a distribution network equipment of a utility in the field are maintained. Precise location and engineering information are maintained. This is important for network planning, crew management, breakdown analysis, vegetation management, and giving efficient customer service. For example, with this system, we can give a cable jointer the precise location map which indicate the location of a joint with proper distance and bearing reference to the nearby identifiable objects. So it's easy to find the location of an asset. And since it is based on the geography, we can analyze, for example, we can analyze lighting strike data within the service area and decide where to focus lighting protection, lightning arresters to prevent outages due to lightning. So this is the type of network implemented in a digitized map on top of the physical geographical map. Now, you may be able to remember we use a term called network reconfiguration. Here, among the system operation application, there is a word called network reconfiguration. This is a method of system operation. During system operation, we use that network reconfiguration method. What it means? So, we'll discuss more about that. Network reconfiguration of a distribution system is an operation to alter the topological structure of the distribution feeders by changing open and closed status of switches. If you can remember, at the beginning I show you distribution network structure. There were several switches along the ring and even in the radial network. What we can do is we can change the open or closed status of those switches. For what? It depends on the adjustment of the switches depend on the type of the objective function adapted. For what objectives we switch those switches. For example, we do switching or network reconfiguration to reduce the power loss according to the load pattern. Okay? To improve the voltage profile and to balance feeder load and lighten overload condition of the network by transferring load from the heavily loaded feeders to the lightly loaded feeders. If we find that when we supply power from a particular direction, the network voltage levels are going down, what we can do is we can feed the network from other direction, or we can shorten the feeder length. and we can shorten one feed and extend one feed. So I think you can understand what I mean. So if it is in a ring, we can lower for the low voltage side, we can reduce the feed length by switching off one section and add that section to a feeder which has good voltage profile. Then we are going to talk about information management method in the distribution management system. When number of applications in a distribution management system are higher, managing the information and maintaining the DMS become a challenge. For example, in North Central Province, we had transformers over 200. It's close to 3,000. So if we get the information about transformer power, power import, power export, current in three phases, voltages in three phases, and power factor, like that, there are many inputs. So into 3,000. So it's not easy because there are a lot of data coming from the network. If we consider the customer-wise data, voltage, current, and power consumption data, it's a huge information load. So it's maintaining such data is a challenge. So for that one, standardized models such as common information models were developed to information management. The IC standard 61970-31301 and 61968-11 are collectively known as the Common Information Model for Power Systems. And IEC 6196811 2013 version specifies the distribution extension of a common information model is specified in IEC 61970 and 301. So common information model allow application software to exchange information about an electrical network. It allow application software to exchange information about an electrical network. CI, Common Information Model, facilitates the integration of network applications developed independently by different vendors by defining a common language. There may be applications developed independently by different vendors. So CIMM facilitates the integration of network applications developed independently by different vendors by defining a common language. It describes the component of a power system at an electrical level and the relationship between each component. Provide standard way of representing the power system resources as object classes and attributes along with their relationships. And important thing is that enable application of systems to access data and exchange information independent of how much such information is represented internally. Despite how the information is represented internally, they can exchange data and information independent of the internal information represented methodology. So these are, if you are willing to learn more, these are the IEEE standard sections in that IEC 61968 2021 part 1 says interface architecture and general recommendations, and part 2 is about procedural terms, and part 3 interface for network operations, part 4 interface for record and access management, part 6 interfaces for maintenance and construction, part 8 interfaces for customer operation, And part 9, interfaces for meter reading and control. And part 11 is the common information model extension for distribution. Part 900, guidance for implementation of 61968. You can go to this one. Common information model profiles are given in part 13. Part 100, IC implementation profiles for application integration. And part 9, interfaces for meter reading and control. So you can go to this one if you are interested. And SCADA, supervisory control and data acquisition. SCADA is a system of software and hardware element that allows organizations to monitor, gather, and process real-time data and control access locally or at remote locations. Directly interact with devices such as sensors to human-machine interface software and record event into a log file. These are the functions of SCADA. For data acquisition in SCADA, input-output modules connected to distribution equipment gather the field parameters. What are the field parameters? Status of switches, circuit breakers, status of transformers, capacitors and batteries, and voltage and current magnitudes, like that. The remote terminal units collect input-output data and transfer them to the remote master unit via network interface modules. What's the RTO? It's a microprocessor control electronic device that interfaces object in the physical world to SCADA system. The central control unit receives, analyzes, and generates the control actions. RTUs transfer messages from the master supervisory system back to control the connected objects. Features of SCADA: monitoring, event processing, and alarm. Central control unit compare the measured data to normal values and the limits. For example, it monitors the overload status of an equipment, transformer and feeder circuit, and if there are any violations in voltage limits. Detect the changes of status of switchgear and operation of a protection relay. An event is generated if there is change of switchgear or status or violation of circuitry. An event is generated if there is a change in switchgear status or violation of a circuit limit described above. So all events generated are processed by the event processing function. Then deliver appropriate information to the system operators to the human machine interface HMI. The most critical events will be sent to the operators as alarms, flashing color representation of audible signals or audible signals. Control in SCADA. Control through SCADA system can be initiated manually or automatically. For example, if we want to switch off a particular place, we can switch off that device. But further, for example, if the voltage level is goes high due to high solar penetration, we can switch off certain device by developing algorithm to cut off those feeders automatically. Control initiated manually can be direct control of a particular device, for example, circuit breaker or a tap changer. Local control logic is used to ensure the equipment is operated following a specific sequence or within a specific limit. When functions are initiated manually by the control operator. Control initiated automatically is triggered by an event or specific time. Data storage, event log, analysis and reporting. Real-time measurements are stored in real-time database of the SCADA system at the time received. Because the data updates overrides all values with new ones, the time tag data is stored in the historical database at periodic intervals. For example, every 5 minutes or every hour for future use. For example, North Central Province, when I was work there, we gather distribution transformer load values and current voltages, power factor, import export power in every 15 minutes interval. So there's a time tag data in every 15 minutes interval for every distribution transformer. You can access them to Office. And we can use those data for various planning activities and identification of fault, overloaded conditions, like that. Advantages of implementing SCADA system for electrical distribution. Continuous monitoring and control of distribution network is performed from remote locations. We can continuously monitor and control the distribution network from a remote location. It saves labor costs by eliminating manual operation of distribution equipment. Otherwise, we have to go to the location and switch on off. It takes a lot of time, particularly because distribution networks are distributed in vast area. It's traveling place to place takes a lot of time, so we can avoid that one by doing control by a SCADA network through a SCADA network. Due to timely recognition of fault, equipment damage can be avoided. If we can timely recognize the fault, we can isolate those sections and avoid equipment damage. Reduce the outage time by system-wide monitoring and generating alarms so as to address problems quickly. We can have system-wide monitoring and generate alarm to address those issues quickly. Improve the continuity of service by restoring service after the occurrence of fault. Continuity of supply can be achieved by restoring the service after the fault. Automatically improves the voltage provided by power factor correcting and flow control. Facilitate the view of historical data in various ways. As I mentioned before, we can access the historical data, time stamp, so we can use them for various ways. And it reduces the labor cost by reducing the staff required for meter reading. If we can access the meter readings remotely, we can avoid staff required for meter reading as well. At the time I was working in North Central Province in 2003 time, they used to read bulk supply meters remotely, but other customer meters were read manually. Customer information system. What it has inside the customer information system. Metering. Information about metering, billing, payment, losses, quality and reliability of supply, complaint handling. Those informations are inside a customer information system. Regarding metering, it holds inventory of meters and locations. So when there's an issue in the field, we can find we can easily locate that one in the field. Every customer premises has a GPS location, so it's once a person make a complaint, so it's easy to go and find that customer in the field. Regarding billing, it collect meter readings from smart metering system and apply tariff from the customer information database and process billing for all customers and report outstanding information of field collection. And in case of payment, it deliver bills, allow various mode of payment. For example, internet-based payment, budget payment, and it implement credit control and monitoring process. Regarding the losses, real-time or periodic reconciliation of energy purchase, distributed and billed to identify and locate technical and commercial losses. In this way, we can go for where to attend to reduce losses. Quality and reliability of supply. Identify customers affected by outages and provide information to customers regarding outages and their possible duration. And inform customers of scheduled system maintenances. This type of things carried out through customer information systems. And complaint handling. Integrate call center systems and the customer information system. Provide access to customer information. Provide facilities to log complaints. That sort of part there. Sort of things are there for customer information systems. This example is from CEB regarding the applications in DMS. Example of application is the distribution management system. Disconnection assist. This is for disconnection of power when the payments are not done properly. And GeoAssist is to global information system mapping teams. That means all distribution feeders, transformer locations, and 33 kV feeder information are mapped. Breakdown assist, so breakdown field crews. They can select the number of breakdown received, where those are located, what are the type of faults. They can use that application to assist breakdown rectification. And meter assist to meter readers, to meter reading, entering meter reading values, producing bills, that sort of thing. And there are CBKR like applications generated for customers. Now the CBKR has changed to EDLKR, Electric Distribution Distribution Limited Company. So now it has called not CBKR, it's EDLKR. You can still have that CBKR, but the new one is EDLKR. In that application, you can check the account balance. You can pay bills, track your usage, and report issues, take outages. You can, you can lodge breakdown complaint. This kind of application to serve customers. This is breakdown assist application generated for field crews. Staff can break down, attending staff can find number of breakdowns they received and location of those breakdowns, so they can efficiently attend on those breakdowns. And they can report once they finish the breakdown, they can report whether have restored the supply temporarily or permanently, or if there is any other things done later on, they can report them on this application. And later on, we can use those data, analyze fault, what type of faults are coming, if it is related to value clearing, site of the way management, we can attend them separately. Those are low voltage cases or that sort of thing. We can attend on the mitigation methods by using the report produced by these applications. Now, next we are going to talk about modeling and analysis tools. I don't know whether you want to have a small break. 2:20. 1 o'clock. We started at 1 o'clock. Can you stay further? Need to have a break? Or shall we proceed further? Normally, at what time you get a break in this lecture series? Okay. There were two questions. Madam, how do we know export or import in a transformer? There is one question. Now we in a distribution transformer we arrange CTs in a particular way. So direction of the power in or out from that transformer can be captured to the CT, and CT is connected to the meter. When it is import, in that if you can remember the share. Based on the power for direction, it measure it as it indicate as a plus or negative. It captured to the current transformer installed in the distribution transformer. Did I answer your question or not? Is it clear? If we install the CT in the other way, that plus and minus sign will be, I mean, import will be stored as negative and export will be stored as positive pluses. Is it clear? Is that what you want to ask?
Yes,
Clear?
madam.
There was another question. So how I can. Madam, could you please tell what are the specific software tools that can use for modeling and analysis of data? Remaining part of the lecture is we are in that one we are going to talk about that more. And are we going to have a break now or later on? What time you want? About 15 students seems to be there in the lecture. Normally, at what time you get a break? Or are you working without having a break? No idea. In the afternoon. Anyway, you are not talking now. It's actually difficult to carry out lectures remotely. I can't see your faces now whether you got the information clearly or not. Are there any lecturers who do lectures in the uni physically, in the physical mode?
At the moment, no.
Sorry, I can't hear you. Maybe my speakers are low. So yeah, please tell me.
At the moment, there is no physical existence.
Oh, really? What time you normally get the break for this time? This time lectures in the afternoon.
Usually 2:30, around something like that.
Okay, then it's 2:25, so we can have a break. And how long you want to have that break? 10 minutes, like, or 15 minutes? I don't know. 10 or 15 minutes. 15 minutes. So anyway, so now is 2:25. Can you please come back at 2:40? We will start the next section. Thank you. In the meantime, if you have any question, you can write or ask directly. Thank you. Okay, shall we start the lecture again then?
Okay, madam.
Thank you. Now we are going to talk about modeling and analysis tools used in distribution management system. Introduction for that one. Distribution systems were continued to operate with little or no analysis. Still, most of the distribution networks are operate with little or no analysis. Yeah. Now however, there were no much issues as the distribution system were typically over-designed. One reason is that, but nowadays it has become important and necessary to analyze the distribution system as it runs at maximum capacity. And because of these bidirectional power flow issues, we need to have modeling analysis in distribution systems. So we need to model the distribution network equipment in concise and standard form for power system analysis. So now we are going to talk about how to carry out that. First one is topology analysis. Topology of a power system is defined by interconnections among power system components. The relationship between the physical plant model and the power system analysis model is developed by the topology analysis tool. Topology analysis tool does build up the relationship between the physical plant model and the power system analysis model. Topology analysis tool carries out network reduction. With an example, you will understand this one. Network reduction reduces the amount of data feed into other modeling and analysis tools. Using this topology analysis tool, we can reduce the amount of data feeding to modeling and analysis tools. For example, zero impedance connection, a circuit breaker, an isolator, or a very short cable, it is in one state, will merge into one node. You can see here transformer, short cable, circuit breakers, isolators, these all things come together and make one node. So the transformer is there, this bus bar is there, and the load is there. So all these things become a one node. The topology analysis tool is able to distinguish the energized part of the power system from the de-energized part and can identify the electrically separated island. The physical plant model with 54 bus bars and the equivalent power system analysis model with only 13 nodes derived from the topological tool. See, actual physical configuration of the network is shown here. It has 54 bus bars. If you count, you can see it's given here. It has 54 bus bars. And equivalent model only have 13 nodes. See, this one node, After short cable, it's second node. Then after that, we have circuit breaker, two circuit breakers there, and again there's a circuit breaker here, switch here, and this is the load. All these things has made this A node here. See, you can see the node A here. How many 6 has become reduced to 1. There were 6 nodes, and finally the topological tool bring it to 1 node. And here also 1 bus and a load, the point B. And the point C here, you can see this is a long cable, so it's there between B and C. But once it come here, that circuit break, three circuit breakers and the bus section, all the things come as 1 node. That is node C and the load there. Again D here, this is a long cable. It is not reduced. C and D, between C and D, there's this 28 and 31 node. So it's keep it as it is. And all these things has make 1 node. 2 circuit breaker, this switch here, and the load. It's the point D. Like that, this one is point E, and F is there. Once it comes to this location, B, and then there's a generator, it's there, and once it comes here, there are 4 circuit breakers and make it to 1 node. This section has become 1 node like that. You can see it has only 13 nodes. Out of these 54 bus bars, it has reduced to 13 nodes using that topological analysis tool. There are specific terms used in a topology analysis. In-feed. In-feed represents the power input from an upstream network that is not modeled. For example, we are not going to model transmission network in a distribution system study. So we represent it by a in-feed, that means power input from upstream. If the in-feed is connected to a bus bar in the physical plant model, an energized island will be obtained if the in-feed status is on. If the in-feed is on, we can identify an island which is energized. If that in-feed status is off, it is de-energized. A link means zero impedance connection between two bus bars. The zero impedance connection between two bus bars. What does it mean? It may be a circuit breaker, or an isolator, or very short cable. Okay. Each link has a status on or off. Circuit breaker can be off or on. A link with only state will merge the two bus bars at each end into one node. If the link is on, the two bus bars become one node. If you can remember in the previous one, here, if the circuit breaker is on, these two become one node. Okay. Nodes are output of the topology analysis. They represent set of bus bars connected by closed link. Nodes are the output of the topology analysis, and they represent set of bus bars connected by closed link. Set of bus bars which are connected by closed link are the nodes. Island are output of the topology analysis. Island are the output of the topology analysis. They represent set of energized node connected by live branches. What are the island? What is called island? It represents set of energized node connected by live branches. That was the output of a topology analysis. This is kind of island. The A, B, C, I, J, K, these are the nodes. They are connected by a line section. These are the nodes. Electrically separate island can be identified and a separate power flow analysis is needed by each island with separate slack node. With the infeed, it's like slack node here. So the slack node is the infeed. So with that infeed or the slack node, we can carry out separate power flow analysis for that particular island. A branch means branch has no non-zero impedance. Branch or the line, it has non-zero impedance. That means it has impedance. For example, it's a overhead line or a cable or a transformer. A branch is live if its status is on and it's a part of energized island, or dead if its status is off, or it's a part of de-energized network. If a branch is live, its status is on. Here, between A and B, these are the branches. A and B, B and G, these sections are the branches. If they are in status is on, it's a part of the energized network. For example, if the branch status is with I and J branch status is O, this is a part of de-energized network, not a part of this energized network. Topology analysis is an input to other DMS applications, and so the performance of topology analysis tool is important in developing real-time DMS. For developing real-time DMS, this topology analysis tool is important. It gives input to other DMS applications. Commonly used graph searching algorithms for topology analysis are depth first and breadth first method. For topology analysis, there are graph searching algorithms are used. That commonly used one are depth first and breadth first methods. This is the depth first search method. Depth first search start at the root and explores as far as possible along each branch before backtracking. See, depth first method start from the root node and explore along that path before backtracking. It go past B and reach D, then backtrack and come to E node. And again in E, it go forward, not go to the I. They explore the flower as far as possible. So E, H, L. Then backtrack. Come here and go to M. There's no way to go. Come back and go to N. Like that. Once it over, it come back to E. From E, it has way to go. EI, then O, then P, like that. Okay. This is an example. See, here we have arrows. So we can go only in this direction. This is an example only. So from this one, if it is depth first search, start from 0 and 2. From 2, then it can go to depth first node, go to 1. From 1, there's no way to go further. So it backtracks. come back to node 2 and go to node 5. 5 nowhere to go there. Nowhere to go. Go back to 2, back to 0, and from there to 4 again. There are many outcomes. So starting from 4, 0, then 4, from 4 to can go to 5, but beyond 5 no way. Go back to 4, again 0, go back to 0, and start to go to 2, and 1, like that. Even it can go to 5 also. The next option is like that. 0, 5, 5 to 4, coming back, go to 4, 5 was already 10 before, go back and go to 2 and go to 1, like that. If you clearly look into this, you will understand how it performs. There are many outcomes, many ways to go. The next one is breadth-first search. Breadth-first search means it begins at the root node and explores all the neighboring nodes. Then for each of those nearest nodes, it explores their unexplored neighboring nodes and so on until it finds the goal. See here, it starts from 0 and go to 1, and it then discover all its neighboring nodes. For 1, the neighboring nodes are 2 and 3. Okay, then there's no other neighboring node. Then it go to the depth. It's 4, from 4, then 5, 6, 7. Those are neighboring nodes. Layer 1 and layer 2 is there. So electricity power distribution system topologies also I want to show you in this section. There are 3 different distribution system topologies. Radial distribution system topology, parallel feeder distribution topology, ring main distribution system topology. There are 3 topologies. Radial distribution system topology is the least expensive one, but its reliability is low. For example, if something happened in this section or here, the power to these consumers will not be delivered. So its reliability is low, but it's less expensive, simple. But parallel feeder distributions also there. There are 2 feeders feeding 1 transformer. This one for this one, it involves high cost, and the reliability improved a lot. For the critical loads, we can use this type of feeder arrangement because there are 2 feeders, load sharing also there, so there will be less losses also. Reliability is high. Ring main distribution system also there. Each distribution transformer is fed with 2 feeders but in different parts. This is the substation. This distribution transformer is fed by this feeder and it travels from here all the way from here to here, and it is fed by this feeder also. So all the distribution transformers have 2 feeding arrangements. It's very reliable method. Normally in town areas like Kandy City, Kalapu City, they have this type of ring main distribution system. Next, we are going to move into power flow analysis. For this one, you need to have a calculator which can calculate complex power. How many of you have calculators in your hand? So I will give you a few minutes, maybe 2 minutes, to bring your calculators to the class. Okay. Now we are going to talk about power flow analysis tool using distribution system model. Power flow analysis provides the steady state solution for a network specific network condition. For a steady state solution is given by load flow analysis. Power flow solution gives the nodal voltages and power flows. We can obtain nodal voltage and power flows using power flow analysis. In a power system, each bus bar is associated with four quantities: the magnitude of voltage and its angle, real power injection, and reactive power injection. For each bus bar, we have a voltage and the voltage angle, voltage magnitude and the voltage angle, and real power consumption and reactive power consumption are there for each bus. For power flow analysis, only two of these quantities are specified, and the remaining two are obtained by the power flow analysis. Depending on the specified and unspecified quantities, the bus bars are classified into three types. The bus bars are classified into three types depending on the known quantities and the quantities to be found out. For example, the slack bus or that in-feed node, which has voltage magnitude and voltage angle. So, but we don't have real and reactive power for that. And PV bus, as the name implied, it has power value and voltage magnitude value, but Q, reactive power component, and the voltage angle is not defined. PQ bus, for the PQ bus, load bus, it has power, active power and reactive power quantities, but it doesn't have voltage magnitude and the angle. Because the distribution feeders are radial, the iterative techniques used for transmission network power flow studies are not used because of the poor convergence reasons. Why they are not converging? Because they have low X to R reactance to resistance ratio in the distribution feed, and they have unbalanced load. And further, there are mix of short line segment with long impedance, long feeders with high impedance. There are short segment with low impedance and long feeders with high impedance. And due to the distributed generators, so due to these reasons, we cannot use the load flow tools which we use in transmission studies. Number of power flow methods have been developed or adapted from transmission power flow methods for analysis of distribution networks. So there are methods which were derived from transmission power flow methods to analyze distribution network. For example, the adapted Newton-Raphson method uses power mismatches at the end of feeders and laterals to deal with the nodal voltages and can accelerate the convergence of the algorithm. This, the adapted Gauss-Seidel method uses the bus impedance matrix to deal with the branch current. The forward-backward method was designed specifically for radial or weakly meshed distribution networks. The method called forward-backward method. It was designed to especially for radial or weakly meshed distribution network analysis. So, this is the method it follows. During the first step, we have two steps, step forward step and the backward step. During step 1, the first forward is sweep, compute the voltage at nodes, assuming no load. During this condition, we calculate the voltage of the nodes in this network. We calculate that one. We assume there's no load in the system. If there is no load, what will happen? The source voltage will be equal to the node voltages. If there is no current, in-feed voltage or the supply in voltage is equal to the source and equal voltage is equal to the supply in load and voltage here. Since there is no current flow, there is no voltage flow. So during the forward sweep, we calculate voltages in the nodes, and during the backward sweep, starting from the farthest away bus, we calculate the current using the calculated voltages above. We start from the start from the end and calculate the things backward. So for that one, the equation we use is I is equal to apparent power divided by voltage vector and get the conjugate of that one. After calculating the current, then we calculate voltages from the source end to the load end. For that one, we use Kirchhoff voltage law to calculate the current node starting from the source end using the current calculated during the backward sweep. For that one, we use the current calculated in backward sweep to calculate the voltage at forward sweep continue by applying Kirchhoff voltage law to calculate the voltage at node starting from the source end up to the load end. For that one, we use the current calculated in the previous backward sweep. Then what we do is we can find whether the convergence is achieved when all the phase voltages at all nodes satisfy Vn means the currently find voltages, and Vn minus 1 is the voltages at the previous iteration, and divided by nominal voltage and get the value. And if it is within the specified tolerance, we can stop iterations, carrying out further iterations. So you will understand the thing with this example rather than saying inverse. So there are 3 buses in this network. This is the input node or the slack bus. The voltage there is 7200 and the angle is 0 is the reference point. And bus 2, there is a load connected to bus 2. That load is 1500 real power and 750 reactive power. And here in bus number 3, the load is 900 plus the reactive power component is 500 here. So the impedance of the line is given here, Z12 from here to here. Z values are 0.1705 plus imaginary part 0.3409. So we can get that one angular coordinate from 0.381, angle is 63.43. And Z23 also 0.2273 plus the imaginary part is 0.4545 ohm. And if we convert that one to the polar coordinate one, 0.508, angle is 63.43 ohm. So now we start the first forward sweep. This is the first step of our calculation. Here what we assume, if you can remember, I mentioned in this first forward sweep, we assume all the buses in the network having the same voltage as slack bus voltage. So the voltage at bus 2 and bus 3 are equal to the bus voltage at bus number 1 or slack bus 7200. Since there is no current, we can apply that current voltage law. V2 is equal to V1 minus Z12 into I12. But since I12 is 0, V2 is equal to V1. There is no load in the system. That's what we assume. So V1 equal to V2 equal to V3. Also like that, similarly, there is no current in the no load condition in the system. So V3 is equal to V2 minus Z23 into I23. Since I23 is 0, V3 is equal to even V2. So now we found that V1, V2, V3 is equal to slack bus voltage, that is 7200 volts. So now this is the end of forward sweep. Now we have to start the backward sweep. To calculate the during the backward sweep, we calculate the currents. The first backward sweep. So during this one, we use the voltages calculated in the previous iteration. Anyway, it was same for the whole bus 2 and bus 3. It is 7200. Now to calculate the current, we use this formula. Is Samara VI conjugate? No, we get the I of that one. I is equal to S3 over V3 and conjugate of that one. So we know what is the S3 value. It was given here 900 plus J500 And since they were in megawatt, so they were in kilowatt, I guess. It's multiplied by 1000. And V3 value is equal to slack bus voltage 7200. So divide S3 by V3 and get the conjugate of that one. We could find I3 is equal to 142.999. Then the angle is minus 29.05 amp. And which is equal to I3 value is equal to I23, the current flow in this bus bar. Now, once we have that one, we can calculate next. So, we calculated what is the I3 value and I2 value. You have not missed the things. What we did first was assume no load condition and calculate the voltages of the three nodes that is equal to the slack bus voltage. Bus 2 voltage and bus 2 voltage is equal to the slack bus voltage. Then the second step is the first backward sweep. Use the voltages calculated before and calculate the current starting from the last end. From here, bus number 3. I3 is equal to S3 over V3, and using that formula, we calculated I3 value, but this is equal to I23. I23 means current flow in this bus bar. Now, using that one and for applying this equation to the bus number 2, we can find what is I2, S2 over V2, we got the conjugate that one, and I2 is equal to 232.9 to the angle at 26.56. And what is I23? The current flow in bus number 1 between 1 and 2, which is equal to the I23 plus this current in this load. Since we have found everything here, we can add these two together, and the final value is I12 is equal to 375.83, and the angle is minus 27.51. So this one is the first backward sweep. Then what we do is we calculate the second forward sweep with new currents. Earlier we calculate the first forward sweep, assuming then there is no current. So that's why we end up with the slack bus voltage equal to bus voltage 1 and bus voltage 2 and bus voltage 3. Now it's different. Now we have current values which we have calculated during the first backward sweep. So now we have to use those current values to calculate voltage values in the bus bars. If we write the equations, V2 is equal to V1 minus Z12 into I12. If you want to find the voltage at bus 2, which is equal to slack bus voltage minus voltage drop in this section, that is equal to Z12 into I12. Now everything is there. We have already find values of I12. V1 is equal to slack bus voltage 7200 and the angle 0 minus Z12. Z12 means the impedance in bus section 1 and 2. which is given there as a data, which is equal to 0.381 into angle 63.43 ohm. Okay. Now, oh, sorry. Here, this is this is the impedance value which is given here, and then the current value. Current value which we have already calculated as I12, and we can apply it here. 375.83, and the angle is minus 27.51. And once we do this calculation, we are end up with the V2 value, which is equal to 7,084.04 minus 84I imaginary part. And if we write it in angular coordinate, 7,084.54, and the angle is minus 0.68. That is V2. That's the bus bar voltage in this node. And now we need to calculate the bus bar voltage at node 3. V3. V3 is equal to V2 minus Z23 into I23. We have calculated I23 value in the previous slide, and Z123 is given here. So you can apply everything in this formula. V2 is equal to the value we calculated before and insert it there, and Z23 value is given here and multiply it by I23. So you can find what is the V3 value. Okay. The V3 value is 7,024.09 minus 125.097 I, and the angular form is 7,025.2, and the angle is minus 1.02. Now, next step is to use these voltage values and calculate the current in the backward sweep. Before that we calculate whether we have meet the expected error tolerance. So error V3 is equal to V3 calculated this time, V3 calculated before, and divided by nominal voltage. Error for bus bar 3 voltage is 0.0243, but the expected tolerance is 0.0001. We need the things for this accuracy. So since we didn't reach that accuracy, with the expected tolerance, what we do is we need to iterate again. Okay, so at least if one node is not satisfied the criteria, we can stop calculating error for the other bus, because we need to have all the buses have the convergence criteria, expected tolerance. Otherwise, we have to continue. So if we check one is, if we check and find one is not good, then we need not to calculate other error values. Just quit the thing and start doing again. Again, another iteration. So now I invite you to carry out the second backward sweep with new voltage obtained during second forward sweep. Please use your calculator, and these are the voltage values we obtained for V2 and V3. Use these values and calculate the current in the third backward sweep. Is it third backward or second backward? Sorry, second backward sweep. You need to calculate the current in the second. This is the second forward sweep, and for during that one we find what is V2 and what is V3. Now we can use those V2 and V3 values and calculate the current for the second backwards sweep. Starting from node 3, can you please calculate the current? We have voltage at bus bar 3 that is equal to 7025.2, angle is minus 1.02. We know the voltage here, the real and reactive power is given. This is in kVA, so we have to multiply the values by 1000. Use these S value and voltage value. Can you please calculate the backward current? Were you able to understand the process? If not, please raise hand. I will explain it again. It seems you have understand the process. Do I need to explain it again? I think all get the method. So just to outline again. So sorry. We assume no voltage condition in this network and get the bus bar voltages, which is equal to the track bus voltage, using the first forward sweep. Then first backward sweep, using those using those voltage values, we calculate the current values starting from the end node. Bus 3, then bus 2, then bus 1, like that. Next one is the second forward sweep. Using that calculated current, we calculate the voltage starting from the source end for the whole bus 2 and 3. The second backward sweep is remaining. The second backward sweep is remaining. Before that, we calculate the error, whether it is to check expected error is reached. Since we found that it is not achieved, we go for the second forward sweep. Second backward sweep with the new voltage values, we need to calculate the current using the new voltages obtained during the second forward sweep. Can you please start doing this one? I will give you few minutes. We need to calculate the current starting from the load end. Find. So the calculated voltage values before, I will go to that slide and show. So you can use that voltage values and calculate the currents. These are the values we obtained for V2 and V3. Use these values and calculate. Starting from the bus number 3. For bus number 3, what is the equation we use? This is the equation we use. I3 is equal to S3 divided by V3 and get the conjugate of that one. Make sure you multiply the power values by 1000. Since these are given in kilowatt. Sorry, these are the voltage values. Please start. Please calculate I3. I will give you maybe 4 minutes. Can I have the answers you got for the question? I3 value and what's the I3 value you got? You can type in the chat. Thank you for the answers. Yeah, I3 value you will get if you use this expression, which is equal to 146.55, and the angle is minus 30.07. Next, you can calculate I2 value. Were you able to calculate this I2 value? Once you calculate I2 value, you need to find the I12. Okay, that means the current flow in feeder 1 section. You need to get the summation of I2 and I23 value. Samidu Gunaratna has totally different answer. Were you able to see where you get wrong? Maybe a calculation error. Please write down this and you can try again. You will be able to get these answers. Now these are the current values we obtained during the second backward sweep. Next step is to calculate the voltages in the third forward sweep. Calculate the voltages of third forward sweep using the calculated current in this second backward sweep. For this one, the formula what we use is this one, the Kirchhoff voltage law. V2 is equal to V1 minus Z12 into I12. The current values you already obtained. The impedance values are given here. You can find V2, then V3. During the forward sweep, you have to start from the source end. So once you find bus voltage 2, then you can bus 3 voltage you can calculate next. For calculating the bus voltage 3, you need to have the V2 value first. So you can use this formula and calculate the voltage at bus number 2 and 3 using the calculated currents here. Can you please use these values and calculate the voltages starting from the source end? I will give you a few minutes, maybe another 5 minutes to calculate the voltages. If you have find values, please place them in the message. Okay, thank you. Can you please calculate the V3 value also? Thank you for all the people who do the calculation. I think all of you have correct, except minor variation with the decimal places that may be natural. So with these voltage values, what we are going to do next? We need to check whether we have achieved the required conversion. So we calculate the error. Can you do it? So if you can't remember how we did that one, I will show you. This is the way. Here the voltage values we obtained for all the two buses we have to do for bus 1, bus 2 and bus 3. The voltage magnitude we obtained by the previous iteration voltages should be written there, the current iteration value and the previous iteration received value, and divided by nominal voltage. Nominal voltage is 7200 slack bus voltage. So use this equation and calculate error for V3 and error for V2. Please message your answers. Voltage in the current iteration minus voltage in the previous iteration divided by the nominal voltage. So I will go to the slide. We have the voltage values. So you can use them if you have gone wrong. So please calculate the error value and let me know. maybe you want the voltages we calculated in the previous iteration. So this is the voltage values in the latest iteration and the previous iteration voltage values. I will move to that slide. Sorry. Sorry, these are the voltage values in the previous iteration. Can you please show me your error calculations? Voltage magnitude obtained in the current iteration minus the voltage magnitude obtained in the previous iteration divided by the nominal voltage. It is 7200. Please type your answer in the message. Okay, for V3 it's 0.0008. So how about V2? These are the voltage values we calculated in the previous iteration. I will move to the voltage values we obtain in the current iteration. So please calculate voltage error for V2 also. We need to get both the errors because all the voltage errors should be within the tolerance. Otherwise, we need to repeat the calculation. Find the error for V2 also and please write that one in the message, please. Thank you, Bhamudi. Shall we check your answers? For V3, it's for me, I received it as 0.00079. If the voltage values you use here are a little bit different from these in the decimal places, it could be due to that. Anyway, our expected tolerance is 0.0001. 1. So at the first stage, when we calculate error for bus bar tree, since it is greater than the expected tolerance, we consider the convergence is not achieved. Since it is not true for one of the two buses, we are not going to, we don't want to actually calculate for the second bus anyway, since we have to do the next iteration also. So now we have to go to another round of iterations. So please go for the third backward sweep with new voltages. Please carry on third backward sweep with new voltage. Can you please send me the current values you obtained during the third backward sweep, starting from the load end, far end? Thank you. We'll check the answers. One person has sent his answer. Nirmal. Thank you, Nirmal. Yeah, thank you, Nirmal. Your answer is correct for I3. How about I2 value? What we want is actually I1 2 value. So that is the addition of I2 and I3. Please calculate that one also. Send me the answer. I1 2 value. Please check your answers. I will show you the current values. I2 is equal to 236.83 and the angle is minus 27.24 and I12 is equal to 383.388 and angle is minus 28.32. Please write down these current values. Next, we have to calculate the voltage values. So the fourth sweep. Please write down the I12, I23 and I12 values. Were you able to get these values during the fourth sweep? So please proceed to calculate the voltage error and let me know the error you would for the voltage V2 and V3, please. Abhiran, thank you for the values. So we'll see the values you get with my answers. Yeah, that is correct. So once we calculate error for bus bar voltage 3, we need to calculate the error for bus voltage 3 also. Please calculate for bus voltage 2 also. Please calculate error. V2 is, for V2 it is 1 point, yeah, thank you so much. So now we found that expected tolerance has received for both V2 and V3. Values got less than the expected tolerance. So since we have achieved the convergence, we can stop doing iteration and get these values as the final values. So next topic is network load modeling. The last topic for today. System loads can be categorized into different types. System loads can be categorized into different types depending on how they react to varying system conditions, particularly to system voltage and frequency variations. Voltage dependent load characteristics are important when consider system voltage stability and other static system studies including load flow analysis. There are three basic conventional load characteristics that describe different aspects of load voltage dependencies. What does it mean is there are some loads, their power, real and reactive power consumption is depend on the system voltage at that point. So in the applied voltage. So there are conventionally there are three types of load models: constant current load model, constant impedance load model, and constant power load characteristic. So let me discuss more about that. Load characteristic can be described by the following general form, which is known as the exponential load characteristic. Here, the P is the power consumption at present, and P naught is the power consumption at the reference voltage we know, and V is the present voltage. Q is the reactive power consumption at present, and Q naught is the reactive power consumption at reference voltage V naught. So alpha and beta are the coefficient for voltage dependentness. If we place alpha is equal to 0 and beta is equal to 0, the constant power load model can be obtained. So there, once we place 0 in this place, this whole component become 1. So constant power means whatever the system voltage we apply, it consumes constant power. It doesn't change its power consumption. That's why it's called constant power. Its power consumption is not dependent on the system voltage. So P is equal to P naught, Q is equal to Q naught. Today, many power electronic loads having two converters. A constant DC link voltage is maintained by the first converter, despite grid voltage variation. So, power electronic loads having load characteristics which are close to constant power load characteristics. Constant current load. Constant current load means their power consumption is proportional to the applied voltage. So to obtain that load model, we can apply alpha is equal to 1 and beta is equal to 1. So the power consumption is proportional to the applied voltage. So the current consumption, constant current means the current consumption remains same despite the voltage changes. But the power consumption depends on the applied voltage. Then the constant impedance load, like resistors. For that one, we apply alpha and beta is equal to 2. Once we apply that one, power is equal to reference power into V over V naught, reference voltage. V means the present voltage, V naught is the reference voltage, to the power 2. So resistive loads behave as constant impedance loads. But in reality, there are very less pure constant power, constant current, and constant impedance loads. What we can see is they are having combination of these three characteristics. So it is shown by the SIP load model. It has constant impedance part, constant current part, plus constant power part. So the A naught, A1, A2 are the proportions of constant power, constant current, and constant impedance components. But in reality, many practical loads exhibit different alpha and beta other than 0, 1, and 2. If we go to the literature, we can find these alpha and beta values in a vast range. So, at the moment, at the time, numerous sophisticated loads are merging into power systems continually, replacing the conventional system loads, making and which make accurate system studies challenging than ever before. When we have voltage dependent load, when we carry out power flow studies, we have to look into those characteristics. If the load is a constant power load, its power value doesn't change with the applied voltage. So for all iterations, real and reactive power values remain the same despite changes in the node voltages. But with voltage dependent loads, if we consider constant current load, its power consumption is proportional to the applied voltage. So if we consider the previous calculation for S3 for first backward sweep is 900 plus J500, because voltage is equal to the base voltage. For the second backward sweep, we need to apply this criteria there, that is P naught base power into V present voltage divided by previous reference voltage. Once you calculate this one, you will be end up with this expression. So I31 is equal to I1. That means constant current load means even the voltage is varied, it doesn't affect the current value, it remains the same. So constant current consume constant current load consume constant current despite the node voltage variation. Even in different iterations, the voltage values are changing, but since this is a constant current load, it doesn't change its current consumption. Next thing is what will happen to the load flow studies when we have constant impedance load. Here, the load power consumption is proportional to the square of the applied voltage. So, for the calculation of S3 for the first backward sweep, it is the same because V equal to V base. For the second backward sweep, we need to calculate using this expression. So all subsequent iteration, new S values should be obtained using the voltage calculated in the forward sweep before calculating the current in the backward sweep. So this is the end for today. So I want to show you one previous exam paper and answers for that. This is the question given for 2022 exam. You can quickly write down this stuff. I will give you the answers. You can do it as homework or now itself. Whatever you prefer, that I can stay until you do. Can you please write down this 1.5 question? Please draw the network and these are for unit values. There were questions regarding the recording and the lecture notes. Definitely, I will upload that one to Fields by today, most probably by today afternoon. If you have any questions, in the meantime, you can ask. You can see the answers. Please try whether you can get these answers. Were you able to get these answers? I think you have got enough time to check the write down the answers. I don't know whether you have tried it now itself. If not, please try to do that one later on. And there's one assignment also for this section. I will that one also to the fields. How long do I need to give it to you to complete that? Maybe how about 2 weeks? Is it enough to have 2 weeks to complete a simple assignment, not the big one? Anyway, do you have any other questions related to today's section? Is there anyone from former CEB? We have several companies now.
Yes, madam.
Yes, Abhirat. Is it Abhirat?
Yes, madam.
Where do you work?
I work as a project engineer in NTNSP.
Oh, really? Okay, we know that. You recently joined or long ago?
Now there's 1 year.
One.
Last year May.
Okay, okay. Nice to hear about you. Do you have any questions related to this content or any other? If I know, I will explain. If there is no other questions, you can try this question for the rest of time, and please raise any question if you have regarding the content I covered. So thank you so much for active participation today.
Thank you.
Thank you, madam.